minute or two, wait for people to show up. All right, we'll get started. All right, so I hope everyone's had a good week and that your first exam went well. We're gonna try and keep it pretty quick today so that we can get you out. So today we're gonna be talking about alkene stability, carbocation stability, Bronsted acid base stability, and then comparing boiling points. So it seems like a lot, but I think we should be able to tackle it in a fairly fast pace. So let's get started. So if everyone will agree, these are 3 different alkenes, and they all have the same number of carbons. So nothing has changed about that, except for the way that the carbons are arranged around the double bond. So can anyone tell me what you notice about these 2 molecules, the relationship between these 2 molecules? Anything at all?
Wait, can you repeat the question, please?
Sure. So could you tell me something you notice about the relationship between these molecules? Go ahead.
As you get more alkyl groups, like attached alkyl groups, you just get a lower heat of formation.
Good. And so does a lower heat of formation mean it's more or less stable?
More
Stable. Perfect. Yeah. So as Nestor pointed out, as you increase the number of attached alkyl groups at the double bond, your heat of formation decreases, meaning that the molecule itself becomes more stable. So let's just take a look. So yeah, so as I said, stability increases with increasing number of alkyl groups attached at the double bond. And so let's look at why. So this might horrify you. Just a little throwback to Gen Chem. So if you remember that hybrid orbitals are made when the s orbital and the p orbitals combine in different forms, right? So when you get, say, sp3, that's saying that it's 1 part s and 3 parts p. Okay, so and 2 is 1 part s and 2 parts p, and then sp is 1 part s and 1 part p. So as the ratio gets smaller, right? So we have, say, 50-50 when we get to SP, right? That means you're going to have 50% S character and 50% P character. And so because the S orbitals are lower in energy than the P orbitals, hybrid orbitals with more S character are going to be lower in energy. right? So we see the orbitals combining to make sp3, which is the highest of the hybridized orbitals, and then sp2 and sp. Okay, so let's keep that in mind when we think about alkenes, right? And so, right, we have in the first molecule, we have one alkyl group attached at the double bond right here. And in this bottom molecule, we have the one up here and the one down here, right? And so what we actually do by adding alkyl groups around the double bond is we're actually increasing the number of C bonds. Now, that might seem, oops, that might seem a little weird, but we'll take a look and see what that means, okay? So if we look at the hybridization at, say, this carbon right here, can anyone tell me what the hybridization of that carbon is?
sp2.
sp2, good. And how about this one?
sp3.
Good. And this one?
sp3.
sp3, good. Okay, so if we compare these bonds, right? So let's compare this bond with this bond, right? So in this case, we have a carbon-carbon bond between a carbon sp2 and a carbon sp3. And in this bond up here, we have a carbon sp3 with a carbon sp3. So that's what that notation means, the CSP2 and CSP3. Okay, so if we think back to the last slide with the hybridizations, right? Is a CSP2 CSP3 bond going to be stronger, or is a CSP3 CSP3 bond going to be stronger?
The CSP2 CSP3.
Cool. And can you give me a possible reason why?
Because there's more S character. So
Exactly. Perfect. Yeah, that's awesome. Okay, so in this bond right here, right, you have more S character with the hybridized sp2 carbon. And so, as we know, that is lower in energy. And so that results in a shorter bond and a more stable bond between these two carbons compared with the CSP3 bond. Okay, so the sp3 is the highest energy hybrid orbital, and so a bond between two things that are sp3 in terms of carbons is going to be less stable and less strong than that CSP2 CSP3. So what we do when we increase the number of alkyl groups around the double bond is we're increasing the number of CSP2 CSP3 bonds that are present in the molecule. And so that leads to an overall stabilization of the molecule because you have, greater S character involved in those bonds that are made, okay? So, and here is a general order of stability. And remember, R groups just means the rest of the molecule, usually implying that it's just some sort of carbon chain or carbon whatever attached to it, okay? So as you increase the number of carbons or the number of alkyl groups around the double bond, you increase stability. But let's also just one quick point about this one in the box. Okay, so in this one right here, we have the R group cis, and in this one right here, we have the R groups trans, and the trans molecule is going to be more stable than the cis molecule because of when you have these groups cis, you have a greater likelihood that you'll have steric interactions that destabilize the molecule. So you have overlap of electron clouds, and that will lead to the destabilization of the molecule. So it's very similar to the reason why in the chair conformations, when you have larger or substituents, generally to stabilize the molecule, those will want to be equatorial to prevent those sort of steric interactions up top. Same thing here. So trans is going to be more stable than cis. Any questions on this stuff?
Yeah, can you repeat the reason, please? I didn't understand why the reasoning.
For cis versus trans?
Yeah.
Okay, yeah, sure. So if we think about, I'm just gonna oops, say something like, let's just imagine we have this, right? Or just let me give you an example. So let's just look at so here's a simple example. Okay, so if you notice in the cis molecule, you have these sort of interactions up here in the middle, right? And so these, you'll have like van der Waals repulsions here, okay? And so you want to reduce those repulsive forces because the presence of those forces leads to the destabilization of the molecule. Okay, so if you have a trans, you have these groups basically pointed away from each other. And so you reduce that harmful interaction that we see up here in the center. Does that answer your question?
Yes.
Okay, good. All right. So we're not gonna take a long time to do these. I just kind of want you to think about like your gut instinct, okay? So maybe take like 30 seconds to look at these and come up with an answer in your head, and then we'll just run through them really quickly. Okay, so can anyone tell me what they think for A? Which molecule is going to be more stable?
The one on the left.
Yeah.
Good, yep. So the one on the left is gonna be more stable. Can you tell me why you thought that?
Because there's three, like, there's three sp2, sp3 bonds versus the one on the right, which only
Good,
has
yeah.
two.
Perfect. So if we compare, say, this methyl group sticking off and this methyl group sticking off, right? This one right here is involved in a CSP2, CSP3 bond, whereas this one on the right is CSP3, CSP3, okay? So we've increased the number of alkyl groups around the double bond in the one on the left. Good. Can anyone tell me what you think for B?
The right one is more stable
Good. Can you tell me why?
because it's trans.
Perfect. Yep. So in this right here, right, you have this big, big clunky thing, and this up top, right? So you're going to have some negative interactions in here, whereas in trans, you have these big groups away from each other. Good. So the right one's going to be more stable. Okay. So now we're going to talk a little bit about carbocation stability. And so just to review some terminology before we get into it. Okay. So if we look at this first one on the left, this is called the primary carbocation, or it's often denoted with that like first degree, but it's also known as primary. And then the two degree is secondary. And finally, tertiary. Okay, so a primary carbocation is one in which there is only one alkyl group around the carbon with the positive charge. And then secondary carbocation has two alkyl groups around the carbon with the positive charge. And lastly, the tertiary has three alkyl groups around the carbon with the positive charge, okay? And so if you'll notice from this arrangement that the tertiary carbocation is the most stable of the carbocations, okay? And so we're gonna first look at a reaction, and then we'll talk a little bit about the stability further, okay? So if we look at this reaction, okay, so the first step in this reaction is we're going to have the electrons from the pi bond actually attack the hydrogen, which releases the bromine by itself. So you get a bromine atom, bromine anion, and a new single bond or sigma bond is going to be formed with that hydrogen. Okay, so two possibilities theoretically can arise from the situation, because we don't in theory know which carbon, whether it's going to be this one in the middle or this one on the outside, is actually going to be taking the hydrogen. Okay, so two possibilities are we have CH3. Okay, so we can either have the hydrogen attach here or here, okay? And so in the case of the one on the left, we have formed a primary carbocation, right? Because if we look at this carbon, we only have one alkyl group attached to it. And in this one, we've formed a tertiary carbocation, okay? Because we had the hydrogen attach at the carbon on the outside as opposed to the middle one. So with this, right, we also have a Br minus present in solution. And what this is going to do is this is going to attack at the carbocation, right? So it's going to attack at the carbon with the positive charge. And the result of that is going to be, in this case, we have so this is the result of the bromine attacking the carbocation, okay? And so it actually turns out that none of the one on the left forms, and the exclusive product is the one on the right. Okay, so the scenario in which a primary carbocation was formed does not happen. It's not observed. So the only one that it's observed is when the tertiary carbocation formed in solution. Okay, none of that product on the left is found. Okay, so let's just take a look at a couple more molecules, and then we'll get to the reasons why. Okay, so if we compare these two molecules, the one on the left is a tertiary carbocation, and the one on the right is a primary carbocation. And the heat of formation of this one is 690 kilojoules per mole. And for the one on the right, we have 845 kilojoules per mole. And so based on this, we see that the one on the left is 155 kilojoules per mole more stable than the one on the right. Okay, and so this can sort of be generalized that it's about 78 kilojoules per mole of stability per alkyl group that you attach at the double bond. Okay, and I mean not the double bond, the carbon with the positive charge. Okay, so this is just showing you that the tertiary carbocation is significantly more stable than the primary carbocation. All right, and so the last thing we're going to talk about is why this is the case. Okay, and this is going to seem a little strange, and just know that this phenomenon exists, but you don't really need to know it in depth. It doesn't ever really show up on exams. Okay, but it's good to know why. Okay, so it's the reason tertiary carbocations are so much more stable is because of this phenomenon called hyperconjugation. And so if we look at this, right, we have it's this molecule, right? CH3. So it's the same molecule from the previous page, and the carbon with the positive charge has a free p orbital. Okay, there aren't any electrons in this p orbital, right? And so that's what we're showing by this positive charge right here. Now, the carbons on the outsides, which are bonded to the hydrogens, right? So we have these hybrid orbitals like here, bonding with the hydrogens. And so what actually happens is the bonding orbital, the electrons in the bonding orbital overlap some with the free p orbital on the carbocation, okay? And so you get some sort of overlap between these bonds right here, right? Well, like this whole thing, right? So because the p orbital is so electron deficient and you have this overlap, that overlap with the empty 2p orbital is basically like it's participating in additional bonding. And so that like additional bonding provides a stabilizing effect for this molecule, okay? And so for this tertiary carbocation, we have 3 hyperconjugation interactions. All right, so we have 1, 2, 3. Okay. And so this is basically the concept. Okay, you have an overlap of basically exterior bonds around the free p orbital, and due to the overlap, some electron density can be donated because of that overlap, and that acts as, we can call it like additional bonding, and so that stabilizes the carbocation. And this is really the explanation as to why tertiary carbocations are the most stable of the 3 different types of carbocations. Okay.
In this
So,
image,
yeah.
I have a question.
Sorry, but yeah.
In the image, you said there's an interaction of 3 p orbitals, but I only see 1 p orbital.
I'm sorry, I had to turn my computer up. Can you say that again?
Is it interaction of 3 p orbitals? That's what you said. I'm confused. I only see 1 p orbital.
Sorry. No, so it's the overlap of these bonds right here, these 3 bonds with the single p orbital in the middle, right? So the p orbital, if you want to think about it, like has this sort of like thing like this right in the middle. And so when you have these bonds right here, right, here, here, and here, the electrons that are in this these bonds overlap with this like p orbital, and so it's just the single p orbital with the 3 bonds around it from the external carbons. Does that make sense?
Yeah.
Okay. All right. Are there any other questions on this? No? Okay. So this is all I have today. So I'm going to turn it over to Corel, and he'll pick up where I left off. So.
Hi, guys. All right. So we're just going to continue with kind of carbocations and what we've been talking about so far. If at any point you can't hear me, please just unmute yourself and yell at me, and I'll try to get that fixed. So as Brandon was talking about, we were talking about carbocations and how the more alkyl groups you have attached to your carbocations, the more stable they're going to be. So on that note, there are things called hydride and methyl shifts that are employed throughout chemistry, organic chemistry specifically, that allow you to stabilize these carbocations more. So in order to stabilize carbocations, molecules can undergo changes known as hydride and methyl shifts that bring forth a more stable carbocation. And these hydride and methyl shifts kind of occur through the movement of electrons into the empty p orbitals of the carbocation. So the empty p orbitals that we saw on the carbons where that positive charge was resting. So let's kind of show an example of a hydride shift. Let's see what this looks like. So if we have a carbon, and kind of in the back we have this methyl group attached. We have another methyl group attached right here, a hydrogen right here. And then we're going to just continue this with a CH3 and H, and then we have our empty p orbital right here where that positive charge is. So what can actually happen in this is that you can get the electrons that are between that carbon-hydrogen bond. You can get them to shift over into that empty p orbital. And what that's going to do is it's going to pull not only the electrons, but also the hydrogen that's attached to that carbon it's going to pull it and pull it onto the other carbon. And what that's going to look like is it's going to change the molecule into something like this. So now you're going to still have your methyl groups attached to that carbon, and you're going to have the second carbon, but now this carbon is going to have a methyl group, a hydrogen, and another methyl group attached to it. Actually, sorry, a hydrogen attached to it. So it'll have two hydrogens and then a methyl group. And the last thing is that now your positive charge is going to be on your leftmost carbon, or your left kind of middle bonding carbon. And can someone tell me what's the difference between this carbocation, carbocation 1, and carbocation 2? So what type of carbocation do we have right here? Is it a primary, a secondary, or a tertiary carbocation?
A primary?
Close.
The secondary?
Yeah, secondary, right? Because we have a methyl group attached to it, so that's 1, and then another carbon-based thing attached to it, so that's 2. So now we have a secondary carbocation. That's what we started with. Now, what kind of carbocation do we create after the shift? So what kind of carbocation is, not that one, what kind of carbocation is that now?
Tertiary?
Yeah, exactly. So by doing this hydride shift, right, just moving that hydrogen, what we are able to do is we are able to go from a secondary carbocation to a tertiary carbocation. And based on what Brendan was just talking about, we know that the tertiary carbocation is going to be the more stable carbocation. So by doing this hydride shift, we're able to make one carbocation and turn it into another carbocation to make a more stable carbocation. And another important thing to note is that the p orbital, this one right here, the one that has your empty that empty p orbital that has that positive charge, it has to be parallel with whatever group you're trying to kind of shift electrons into. So if it's not parallel, you can't pull those electrons into that p orbital. So in this example, right, our empty p orbital is on the plane of the screen, and so is our hydrogen because it has that line attached to it. So does anyone have any questions on hydride shifts?
I actually have a question. What is the difference between a resonance structure and like a hydride shift or a methyl shift?
Yeah, so a resonance structure, right? We are keeping all of our atoms in the same place, but we're moving the electrons around. In this hydride shift, what we're doing is we're not only moving our atom, right? We're moving the hydrogen to the other carbon, right? It's now being moved to that carbon, but we're also moving the electrons. So with this hydride shift, we're moving both atoms and the electrons versus resonance structure, we're only moving the electrons. Does that make sense?
Yeah, it does.
Okay.
I have a question.
Yeah.
How do you recognize secondary or secondary I don't know how to pronounce that word, or tertiary?
Yeah, so to recognize them, what you're going to do is you're going to look at you're going to look at your carbon that has that positive charge, and then you're just going to count how many other carbons it's attached to. So in kind of the first example, it's attached to one carbon, right here. and then it's attached to another carbon right there. So that's 2 carbons. So that's why it's going to be a secondary carbocation. In this example, right, the carbon that has the positive charge is the one in blue, and then it's attached to 1 carbon right there on the wedge. It's attached to another carbon on the dash, and then it's attached to a 3rd carbon right there on the line. So that's why it's going to be a tertiary carbocation.
Okay, thank you.
Okay. So now I mentioned that there were also methyl shifts. And so methyl shifts are pretty much exactly like hydride shifts. The only thing that they differ in is that instead of moving hydrogens, we're moving methyls. So let's draw what that's going to look like. We're going to have that. And we're going to have this other methyl group. And it's still going to be attached right there. And then we're going to have our MTP orbital with that positive charge right there. And so the way that we're going to do this is we see that we have this kind of on the plane p orbital right there. And also we have this parallel methyl group right there. And so similar to what we did with the hydride shifts, we're going to draw a curved arrow from that bond into that p orbital on that carbon. And what that's going to do is it's going to change our structure and create this new kind of isomer. So now we have a hydrogen and that methyl are still there, but now we've added in another methyl group on that carbon. And so, let's see. And now our positive charge is going to be on this carbon, on the left carbon. And so, can someone tell me what kind of carbocation did we start with and what carbocation did we end with? Anyone?
We started with secondary,
Mhm.
and we ended with tertiary.
Yeah, exactly. So you see how by doing this methyl shift, we were able to create a more stable carbocation based on these rules of hyperconjugation and how the more alkyl groups you have attached to that carbon with that positive charge, the more stable you can make your carbocation. So, and then just to verify, right, our H3C, it's directly parallel with that MTP orbital. And so because of that, we know that we can do this methyl shift. And I also just want to note that we're not only limited to hydrides and methyls. We can also have other alkyl groups that shift as well. So if maybe instead of having an H3C, we had something like this. H3, maybe we have an ethyl, right? A CH2CH3. And so it's kind of important to know and be able to see when you're able to do when you're able to do these methyl shifts, hydride shifts. This would be an ethyl shift. It's important to know and be able to see when you can do those shifts, because as we kind of get into reactions, it's going to be important to see, can we make a more stable carbocation? Can we do some kind of shift that's going to make the carbocation more stable? And so let's just summarize what we just talked about, right? With our hydride shift here, we draw our curved arrow. Remember to draw curved arrows when you're showing these shifts. You can either, it's generally better to draw them from the bond onto the carbon that you're trying to move to. And so in this first example, they're doing a hydride shift where they're going from this secondary carbocation to this tertiary carbocation. And then in the bottom, they're doing a methyl shift where they're going from this secondary carbocation and going to the secondary carbocation. So with this example, we're trying to illustrate another important point, and that's the fact that although these two are the same energy, they're both secondary carbocations, the fact that they're both equal energy means that they're both equally favorable. So when you have reactions, you can have a mix of products because you can have these kind of the positive charge on two different carbons that are equally favorable. And so it's also going to be important to know when you can have an equally favorable carbocation versus a carbocation that's more stable. So these are just things that you have to keep in mind. So rearrangements, that's what these methyl and hydride shifts are. They can potentially occur anytime a carbocation is formed. Are there any questions on these rearrangements, any of these shifts?
What does the 1, comma 2 H shift mean?
Yeah, so this is just the terminology. You won't really use it much, but if you think of your carbon as the thing that you're starting from, the thing where you're kind of moving things to, if you think of it as 1, then the thing that that carbon that has that positive charge, you can think of it as 2. So that 1,2H shift just means that you're moving a hydrogen from carbon 1 to carbon 2. Does that answer your question? You don't really have to know 1,2 shift and 1,2 methyl shift.
Okay.
So I have a question. So these two, like for example, in the hydride shift between those two carbocations, those are the same molecule. It just depends on which one's more stable. Like they have the same properties and things like that.
Yeah, yeah.
Okay.
They're actually constitutional isomers, but yeah, you can think of it as kind of having the same chemical properties.
Okay.
All right, so now we just finished talking about how to rank alkene stability and then ranking carbocation stability, including kind of the shifts that you can have to make carbocations more stable. So now we're going to switch gears a little and talk about how to rank Bronsted acid and base stability quantitatively. So just by looking at it rather than having these pKa values that we're generally used to. And so kind of let's just a brief review. Let's just do the first 2. If you are really interested, you can do the third one on your own. But can someone tell me kind of in these reactions, which ones are going to be your Bronsted acid, what's going to be your base? So starting with HCN, is that going to be your acid or your base?
Acid.
Yeah. And then NH2 minus?
Base.
Mm-hmm. And then the CN minus. Does anyone know what that's going to be?
The conjugate base.
Yeah, exactly. And then this NH3 then is going to be your conjugate acid, right? And then for the bottom one, what is this going to be?
The base? Or oh, the base, okay.
Exactly. And then this is going to be your what?
Acid.
Yeah. And then so because of that, this is going to be your conjugate base. And then this is going to be your conjugate acid. Okay, so now that we've done that problem, so just to kind of re-give you that definition of Bronsted-Lowry acids and bases, right? Acids are just going to be your proton donors, so they're going to be giving protons. And then bases are going to be your proton acceptors. Right? They're going to be accepting protons. And so in kind of the general equation, you're going to have something like this, right? And that's going to happen. And then notice that I'm using my curved arrows to show where my electrons are flowing. And so we're going to have our base, we're going to have our acid, then we're going to have our conjugate acid, and then our conjugate base. So in kind of this sense, right, what we can also realize is that if we kind of just look at it as a general, that's not how you spell general, general acidity equation, what we'll get is you get this HA, and then when that bond breaks, right, this is just what an acid is doing essentially. You're going to get this H plus and then this A minus, and then kind of bringing back Gen Chem, we'll have that Ka. And so let's consider that the more stable this conjugate base is, then the more the equilibrium is going to favor the product side. So you're going to have Ka is going to be greater than 1, meaning that you're going to have more HA dissociation. Does all of that make sense so far? That the more stable this A minus is, the more the equilibrium is going to lie in that direction. And then point 2 is that the more dissociation of HA, then the stronger HA is going to be. Or you can think of it as the more the equilibrium favors the products, the more H plus you're going to get, making HA a stronger acid. So kind of using that train of thought, we can realize that acidity can be assessed by kind of a couple factors that are going to stabilize that conjugate base. So the more you can stabilize this conjugate base, the more acidic HA is going to be. And kind of these factors are going to be things like electronegativity, size, resonance, polar induction. There's also going to be hybridization, and then charge. And so as we go through, I want you guys to keep this mnemonic in mind, C-A-R-I-O, Cario. All right. So let's first ignore electronegativity trends and let's focus on the C in Cario. So that's going to just stand for your charge. And the way that's going to work is that when you have positive charges, you're able to kind of, those positive charges are going to more likely want to hold the electrons that you would get from deprotonating that atom. So let's just draw that out to make it a little bit easier to understand. So if we had something like OH, H2O, and H3O, or not H3O, yeah, H3O plus. All right, so we know that when we do these acid deprotonation reactions, what we're going to be left with are going to be the electrons that are between whatever molecule you have and your proton. So in doing this, and there's a minus charge right there. So in doing this, right, after you deprotonate, you'd end up with this. Minus 2, minus 1, and there's not going to be any charge on that. So in terms of deciding kind of which one's going to be more stable, right, these pKa values are going to be -1 or which ones are going to be more acidic. The pKa values for kind of these top compounds are going to be -1.7, 14, and then this is just not even going to happen. And so let's think about why this is the case. So we know that when we deprotonate, we're putting electrons onto kind of this anion that's going to be receiving those electrons, right? That's what we said when we had this general kind of acid deprotonation. You're going to get this A minus charge. And so the more negative charge, the more electrons you have to begin with, the harder it's going to be to convince the anion to take even more negative charge. You can think of it as kind of like if you are kind of moving things. And if you already have things in your hand which are synonymous with electrons, right, you're not going to want to have more things. Right? So having a negative charge means you already have a lot in excess of electrons. So by deprotonating, you don't want to have even more electrons. And vice versa, this H3O plus is going to be the most acidic because it's actually at a deficiency of electrons. So it's going to be highly more favorable for it to be deprotonated and gain those electrons that are between those OH bonds. Does that make sense so far? Okay, so that's going to be the first thing that you're going to think about. Carrier, charge. So the next thing is going to be atom, the A. And there's two parts to this. There's going to be electronegativity, and there's going to be size. And so now let's think about this definition, right? When comparing atoms within the same row of the periodic table, the more electronegative that the atom in the conjugate base, the better it is at accepting that negative charge. And what that means is that the more electronegative that atom is, the more it's going to be able to kind of stabilize those negative charges that you're going to get. So let's say you have something like HF, H2O, NH3, let's do NH2 and then do the 3 right there, and then CH3 and then H. So if you kind of recall from the periodic table, the way it's going to work is that you're going to have hydrogens in the first group, and then kind of off in the second group, you're going to have carbon, nitrogen, oxygen, fluorine, and right below, you're going to have phosphorus, sulfur, chlorine, bromine, iodine, iodide, etc. And I just want you to remember that as you go up and to the right of the periodic table, your electronegativity is going to increase. So as you go across, the electronegativity is going to increase. But then as you go down and to the left, the size is going to increase. Size increases, electronegativity increases. So that means that as I go down the periodic table, our size is going to increase. So what that's going to tell us is that between HF, OH, NH2, and then CH3. We're going to look at that center atom that's connected to that proton. We're going to look at that, and we're going to compare whether is it going to be in the same group, or is it going to be in the same period. And so in this first example, we can see that kind of HF, OH, that O right there, the N and the carbon, they're all going to be in that second group. So let's just rewrite that as carbon, nitrogen, oxygen, and fluorine. And so in terms of electronegativity, we know that electronegativity is going to increase that way, meaning that the more electronegative the atom, the more it can stabilize the negative charges that it's going to create from deprotonating. So deprotonating is going to make that. Deprotonating is going to make that. Deprotonating is going to make this. And deprotonating is going to make that. And so based on what we just talked about, right, the most stable acid, the most acidic is going to be this one, this F minus, because it's much more electronegative than the carbon, the nitrogen, and the oxygen. And so that acidity order is going to go like that, meaning hydrofluoric acid is going to be the strongest acid, followed by water, and so on and so forth. So that's kind of the first part of the A in Careo. The second part is size. And so when comparing atoms within the same group of the periodic table, the easier it is for the conjugate base to accommodate negative charge, the lower the charge density is going to be. And so what that means is that as we go down the periodic table, right, your size is going to increase. And so when you have HI, HBr, HCl, and HF, right? When you're thinking about these, HI is going to be the furthest down, followed by Br, followed by Cl, followed by F. And so to see kind of which one is going to be the most, the strongest acid, we're going to look at the stability of that conjugate base. So we have I minus, Br minus, Cl minus, and F minus. And so the bigger the atom is, the more it's going to stabilize that negative charge. You can kind of think about it as the bigger that the atom size, the more it can distribute that negative charge around to make it more stable. So that's why HI is going to be a stronger acid than HBr. HBr is going to be a stronger acid than HCl, and HCl is going to be a stronger acid than HF. Are there any questions on that? Okay. So then moving on to the R in Careo, and that's going to be your resonance effects. And so if we think about this, right, we talked about how the more stable you can make the conjugate base, more stable you can make it, the stronger your acid is going to be. So the stronger this, the more stable this is, the stronger this acid is going to be. And we talked about the one of the things that can stabilize negative charges like that is resonance. So if by using resonance, we're able to stabilize this negative charge, we're able to make this acid stronger. So let's compare something like carboxylic acid. We'll just make that an R group compared to an alcohol. So let's just do ROH. And once again, to see kind of the stability of the conjugate base, let's first deprotonate. And what we're left with is this. Versus this. And those are the conjugate bases of these two acids. And so let's see which one is going to have resonance and which one's not going to have resonance. So if we look at the bottom, right, based on what we've learned in previous lectures, this bottom structure isn't going to have any resonance. There are no pi bonds for me to kind of donate electrons. There's no way for me to move electrons around. But this top one, what I can do is I can move those lone pairs down, and then I can move this double bond up, and then I'll get to this resonance structure. Right? Now I'm going to have my negative charge on that oxygen. And so notice how now that I'm able to kind of stabilize, that negative charge, this negative charge across two electronegative atoms, I'm making this conjugate base, I'm making it more stable. So in terms of acidity, this carboxylic acid is going to be more acidic than this alcohol. And then second to last kind of concept that we have to think about to determine these acidities is going to be the polar inductive effect. And this kind of relates back to what we talked about previously, but essentially the presence of electronegative atoms increases the acidity by inducing electron density towards itself. So let's think about what that means. So if we have something like OH compared to this still OH, but now it has a chlorine at the end, compared to this, right? This still OH, but now it has two chlorines on the end. Right? These are all acids. Now let's see what happens when we deprotonate it to see which conjugate base is going to be most stable. We're going to get this. We're going to get that. And then we're going to have this. Right? So let's just kind of look a little bit through the original mnemonic. So first, the charge is all the same, so we can't really compare that way, right? The charge of all of these conjugate bases and the starting acids are all the same, so we can't say one is going to be stronger than the other right off the bat. Then let's look at the atoms, right? In atoms, we have electronegativity and size. So if we compare kind of those atoms that have that negative charge, they're all the same atoms, so we can't really think that one is going to be more electronegative or one is going to be larger in size. So we can't use that. And then we can ask ourselves the R in caryo, is there going to be any resonance? And there is no resonance in this. So the next thing is the inductive effect. And all that means is that by adding in these electronegative atoms on the ends, you can think of it as kind of creating this dipole where you're pulling electron density away from that negatively charged anion. So when you deprotonate and you get left with that negative charge, the more kind of electron withdrawing groups, that's what these are called, right? Because they're electronegative. The more electronegative groups you have on that acid, the stronger the acid is going to be, the more you're able to stabilize these negative charges. So in terms of acidity, this is going to be more acidic than having one chlorine, and having one chlorine is going to be more acidic than having no chlorine. Does that make sense?
Wait, are you saying that like the electronegative atoms would like want the electrons on the oxygen? Like,
yeah,
okay.
You can think of it as that. They're going to kind of be pulling electron density.
Oh, okay.
Kind of like when you draw your dipoles, you show the electrons kind of being pulled towards a specific location.
Yeah, okay, that makes sense. Thank you.
So that's the polar inductive effect. And now there's just one last thing, right? That's the O in caryo, and that's going to be orbitals. So if you've gone through the C and there's no difference in charge, there's no difference in atom size or electronegativity, no difference in resonance, and they have the same amount of inductive groups, the same amount of these electronegative groups. What you're going to look at now is going to be the orbitals. And so what that means is that the more S character you have in the atom, the stronger the acid is going to be. So the difference between what I have drawn on here, right, is we have an sp3 hybridized kind of, an sp3 hybridized atom that has that proton on it versus an sp2 hybridized atom that has that proton on it versus this sp hybridized atom that has that proton on it. And kind of going back to what Brendan was saying, right? You have greater S character in sp versus sp2 versus sp3. And the more S character you have, right, the closer you're pulling the electrons to yourself. So when we deprotonate these, we're left with H2C minus CH3. We're almost done. You're gonna have that, right? That's what happens when you deprotonate that. And then you're going to have this carbon triple bonded or carbon that has the second hydrogen. So that's what we have. Now, they all have the same charge, right? They all have the same, they're all the same atoms, they're all carbons. So we can't use the C or the A. There is no resonance in these. There's no inductive groups. So now the last thing that we're going to look at is the orbital. So if this is going to be, if we started with an acid that's sp3 versus an acid that's sp2 versus an acid that's sp, what that's going to tell us is that the greater your S character, the more acidic you're going to be. Because the greater the S character, the more you're pulling electrons towards yourself. So the more you're able to pull those electrons towards the nucleus. And the nucleus has those protons that are able to stabilize that negative charge. So then if we look at the pKa's of these, just to verify, we're gonna see that the pKa is 50 versus 42 versus 25. And so based on that, right, we can tell that alkynes, right, these triple bonded carbons are going to be more acidic than alkenes, which are these double bonded carbons, and those are going to be more acidic than alkanes, which are those single bonded carbons. Are there any questions on that? Cool. Now basicity, we can also do the same exact thing for basicity. It's just going to be the opposite. So I will cover that in a really short video along with kind of boiling points. And I will post that tomorrow or Sunday. Are there any questions on kind of how to use these polar inductive effect, resonance, size trends, charge? These are going to be the same thing you're going to use when you're determining which compound is going to be the most basic. It'll just be an opposite. So kind of opposite of what we talked about here. And so I can give like a really brief explanation on that on a video, but just to be respectful of everyone's time, we can end here. What questions are there?
Going back to the